which is so equation of motion for a spring mass system. So usually we use first we use Newton's laws to calculate or to determine the equation of motion of a spring mass system, because when we use F equals ma, then this will give you the equation of motion for a spring mass system. You can also use the Euler-Lagrange equation. So this is in one dimension. So this is this has a 1 degree of freedom. So this is the derivative of the Lagrangian with respect to x minus total derivative with respect to time, the partial derivative n with respect to x dot equals 0. Okay, so this is the first one. You can also do this one. You can also do the Hamiltonian. But this time, for demonstration purposes, we're going to use the conservation of energy. So that means we need to know the kinetic energy and the potential energy of this mass. And from here, we can actually calculate the total energy. And then from the total energy, we can derive the equation of motion if we take the derivative of the total energy with respect to time, and then we equate it to 0. Okay, so we already know from our discussions that the equation of motion for a spring mass system is the mass times the second derivative of position with respect to time plus spring constant k times x, and this is equal to 0. So this is your equation of motion. If we do this, this, or this, which we already demonstrated to you before. How are we going to implement it in MATLAB? So let's have a new script. So this time we're going to use a new live script so that we can see the equations better. Okay, and then let's save this as, for example, let's say for today. So this is 6, 2020. Sorry, June 10 pala, sorry. So the June 10. So let's say 2020. So clear first our workspace, define our functions. Okay, so let me, because we're not going to need the command window anymore because the output will be provided here. So we can move the code here and check this equation, these notes. Okay, so here we need to define the function, the position function x. So sims x, which is, and then we also define m, and we also define set k. Now we set that the velocity function v equal to the derivative. Remember that the velocity function is the derivative of x with respect to time. So that means we define the specific derivative of your position. So I will not go into put a semicolon here so that we can see the output in the cell. Then let's define the potential energy, kinetic energy. So kinetic energy 1/2. So this is times the mass times this velocity. Okay, so let's see. And then potential energy is 1/2. What? Ingat, sino? What's the potential energy for a spring mass system? Uh, Thea. Let's have some interaction. Thea, what's the potential energy of a spring mass system?
One half kx squared.
Okay, very good. So this is 1/2 kx squared. Okay, so let's try first. So here we define the kinetic and potential energy of the system. And when we run, so these are our results. So this is your velocity function. This is your kinetic energy. And this is your potential energy. So therefore, we can define our total energy, which is EC. So again, let's run. Let's just check what happens. So this is the total energy. And then lastly, we can differentiate energy. Okay. And then we equal to 0. Okay. So run. Okay. So as you will notice that this is your equation of motion. So we expect that this is m times the second derivative of x with respect to time plus k times x equals 0. So as you will notice that this is m times the derivative of x with respect to time, second derivative, times derivative of x with respect to time. But, sir, ba't ganun? Merong first derivative pa rin. If we go to notice in the first term, we have kx times the first derivative of x with respect to time. So essentially, this expression, this derivative and this derivative is essentially cancelled. So we arrive at the same equation. Okay?